crisis, emergency, breakdown. There are lots of terms being used in relation to what's happening with the planet's climate, but one thing is certain. Construction industry has a big part to play in reducing global emissions. Recent skyrocketing of energy prices has shown how important it is to reduce energy demands by building better, more efficient buildings. While regulations become more stringent, skills and knowledge to design sustainable architecture will start becoming future mainstream rather than specialist expertise. My name is Luka Stefanovic. I'm an architectural technologist and senior architecture industry specialist at Vectorworks, and I will try to help you understand operational energy in architectural projects right from the early stages.
So a little bit about the context we find ourselves in. You're all probably very well aware of the climate emergency at the moment. The United Nations has its Sustainable Development Goals in order to tackle these emergencies, talking about affordable and clean energy, about sustainable cities, resilient cities and communities. The World Green Building Council has its net zero carbon energy commitment, and advancing net zero carbon challenging the companies, cities, states and regions to reach net zero operating emissions by 2030, and advocating for all buildings to be net zero in operation by 2050. You can see some who already signed up to this, and the list grew longer since I took this image. Buildings have a big part to play in all of this. We're looking at data from Europe, but it's a similar picture worldwide. Buildings account for 40% of total energy consumption and nearly 40% of greenhouse gas emissions. So this is a very much relevant conversation for architects who are realizing more and more their part to play as designers of those buildings. And this is what leads us to Energos, a tool in Vectorworks that allows energy performance evaluation. Now, a typical thing that happens with sustainable design is you have sustainable goals at the early concept design stages, but they then tend to get watered down and lost along the way as the design progresses into developed, then into construction documentation. And by the time the project reaches a specialist consultant, this is the first time that you get actual metrics. These sustainable goals are often lost, and the maneuvering room for any meaningful change is much reduced. That leads me to a comparison with BIM workflows. This is one of the most typical graphs showing the cost of design changes as the time progresses, the effect of those changes can make comparing BIM workflow and traditional workflow. And what we are proposing here is being able to make design decisions early on when they can have more impact and cost much less to implement. I see the path of energy modeling as somewhat of a diversion onto a specialist road and as sort of a parallel process to the main architectural design because it often involves a separate model. This means it's not connected to the main architectural design model and needs to be kept up to date or is done by a consultant. What I'd like to propose is to be fizzing along the avenue of architectural design with regular rest stops during the design at certain points. That would allow us to evaluate the energy performance of the building at various stages of the design, allow us to make informed design decisions and be in control of the process. Let's see it in practice. This workflow presentation consists of 3 parts, simulating stages in architectural design process. Each phase will see us go through different considerations from an energy perspective, as relevant to the level of detail our design is at. We'll start at Schematic Design, where we will explore the design from a conceptual point of view. We will see massing studies and some basic energy settings. We can compare our design options and we can start having a sneak peek into our energy performance. As this is early concept design stage, I've developed some options to explore different configurations I might want to use to express my design intent for this project. I'm using spaces as the objects that I'm doing my massing studies with. Spaces are particularly useful for this kind of early stage concept work, as they're intelligent objects that store various data that can be used later in the project, such as for energy calculations or to create room finishing schedules. I have 4 different design options of a house design, and my 4 options all have the same number of rooms. Those rooms have the same areas, and I'm just moving them around, almost like Legos, to get different configurations while maintaining the same total relevant floor area. So you can see some different design options here and how they have been differently configured while keeping the same balance of areas. Let's just jump back to option 1 now to show how to get our design options to a bare minimum that's needed by Enegos to perform the evaluation. So aside from spaces that will give us the total relevant floor area, we need a building envelope. I'll just select all of the spaces that I have on my ground floor layer so I can wrap them with some walls real quickly. I will create walls from spaces with the space planning set of commands. I can say that I want to create walls from selected space only. I will make sure that my source and my destination layer are correct. Then I can say where I want my exterior walls to be aligned to and place that relative to either wall or the core component. And then I can choose an exterior and interior wall style. And then I can combine collinear interior walls and constrain straight walls to vertical or horizontal if they are within 5 degrees. And I will get my building envelope. Now at this stage, I don't really need interior walls, so I can get rid of them. Then I will select my first floor space, go back to space planning toolset and create walls from spaces once more. Now I will change the source and destination layer. Again, do it for selected spaces only, and the rest will stay the same. I'll say OK, and then we'll wrap our building with walls. So what we now need are slabs. So I can go ahead and pick the walls. Then we want to create the boundary for our slab. Make sure the slab style is the one we want. And make sure that we're on a that the correct design layer is active. And then we'll create the slab. We can repeat the process for the terrace, and we will select the bounding walls. We can go across different floors and design layers. That's not an issue. Just make sure that the active design layer is correct so that the slab will slot in the correct elevation, and make sure that we have the slab style that we want. Then hit the check. and we'll see our terrace slab. And the last thing we need is the roof. Once more, we will repeat the process, change the design layer, and create the slab. Finally, there we go. We have a building envelope and we have spaces so NGOS can work its magic. If we do this for all 4 design options, there is sufficient data to be able to make first rough assessments on the performance of the design options and compare the results. Then we can go to our first rest area, which is the only thing we are interested in evaluating at this stage, and that's because it's the only thing which distinguishes between our 4 design options right now, and that is form. Form factor is defined as the ratio between the building envelope surface and the total usable floor area. The smaller the form factor, the more efficient the shape is, because there is less envelope area to lose the energy through. The more the form approaches a cube, the more efficient it is. Now, I'm not saying that we should be designing cubes all the time, but we can have an understanding as to how the shape affects the performance of our building at these very early stages. And then that can be a factor that informs our choice of 4 different design options. I've created a small worksheet which will tell me the form factor of all of my 4 design options. I can go and edit the report just to show you what kind of criteria I'm using. So I'm filtering objects on option 1 design layer and with a certain wall style that's for my external walls that I'm using for the options. And then I will use component area function and the object type name. Then I will summarize the items with the object type name, which will basically show me all the walls grouped and their surface area. Then I will do the same, show the same criteria for objects on option 1 design layer, and I will just show slab styles. Again, same commands, and that will give me the surface areas of my slab objects. Finally, I will collect the spaces on my option 1 design layer and then I will calculate the area. So that will give me the total floor areas of the spaces. And then for option 2, I will just change the criteria to collect the objects that are coming from the design layer option 2. And then the rest will be the same. So finally, to calculate the form factor, I will add the surfaces of the walls and slabs and divide that by the spaces. So we can see the results and we can see our form factors. So what do these numbers tell us? Remember, the smaller the form factor, the more efficient the shape is. So basically, our option 3 is the least efficient one, and our option 2 is the most efficient one, with option 1 and option 4 in between, option 4 being more efficient than option 1. And if I go back to see my 4 options, that kind of makes sense because I can see that option 2 is the most compact one, and option 3 is the least compact one. Let me just move this wall. Okay, so what I have done here is I've increased the building area surface ever so slightly by twice the half of this wall, but I've doubled my first floor usable space. And then I can ask my worksheet to recalculate, and I'll see that my form factor for option 1 has dropped to 2.4. Okay. And the next thing to look at is wall styles. Now, if you're not using styles in your workflow, I highly recommend you do so. Styles can give you a combination of control and flexibility when working with plugin objects. Some object parameters can be locked to a certain value for consistency, others can be customized for each individual instance to meet the project's needs. It's like a symbol definition for these plugin objects. Enegos needs some inputs regarding the performance of our building envelope. So in the wall style, we have components, and we can assign thicknesses and lambdas to each component. But at this very early concept design stage, we probably don't know the lambdas or thicknesses, or maybe even the materials. So what we can do is a very useful setting that the wall styles have to override the calculated U value, and we can manually input the value. Those can come from building regulations, notional specification numbers if they exist, or we can use passive house recommendations, and if we know what we are striving to achieve, those can be our target values. The final piece of the puzzle, as far as Enegos is concerned, and the last thing that it requires in order to be able to perform the calculations, is the Heliodon object. If you don't have a Heliodon object, one will be automatically added when Enegos project settings are first opened. A Heliodon places natural light in the model, simulating sun. When you enter the location, accurate region or city information is used for the calculations, and Enegos will pull weather data. You can manually edit the city and input the latitude, longitude, and so on for a city if you cannot find it on the list. Let's have a closer look at the properties and the functions of the Heliodon object now. So I will select our Heliodon in the design layer. Vertical and horizontal shadow angles can be automatically calculated for determining the correct placement of shading devices such as awnings or bristles. You need to name walls and copy those names to Heliodon object info, and you can obtain those angles. This is all useful information as you're in the process of shaping the form and need to know where the sun is coming from and at what angles, so you can control the amount of sun coming through a window through the provision of appropriate shading devices. Their efficiency depends on placement and dimensions, and by shading a building or its outdoor spaces, we can reduce summer temperatures, improve comfort, and save energy. We can create solar animation to illustrate the way the sun moves over the model, and shadows are cast upon it as the sun's position changes. Let us go in to the OpenGL options so we can turn the shadows on and see on-ground shadows. Let me move this out of the way so we can see the shadows. I can change the day in the month and the shadows will reflect those changes. Let's actually zoom out so we can have a better perspective and so we can see how each one of our options is casting a shadow on the ground. That's better now. So let's go back to Solar Animation dialog. Solar animations are interactive. We can see the effect in the model as changes are made by moving the slider. We can observe the shadows cast by the model over the course of the day or year and observe the portions of the model that are illuminated by sunlight. If we model context such as surrounding buildings, trees, and other elements, then we could focus on our area of the model, such as a window, to study to determine when, or if, sunshine will affect it. Solar animations can be generated on screen or by exporting to a movie file. We can animate either time during the day or days during the year. We can set the start and end as well as the interval. We can display time and date as text. We can see some basic info and then export this as a short video. Okay, let's go back to OpenGL settings to turn the shadows off. I just wanted to show you how you can still look at solar animations. Notice as I move the slider how the sun rays move over the model during the course of the year or day, and different portions of the model are illuminated by sunlight. Again, this is all relevant information to take into account when making design decisions at early design phases. And finally, we can look at NGOS. I'll open the project settings so we can see we are in the basic range of parameters. We can input the data about our project. We can select a pre-configured setup at this point and for the building. So we can see our building elements list is a very simple, just 10 walls at this point, 2 roofs, 1 slab, no windows, no doors, very crude. The results will be very imprecise at this point, but they will be so for all 4 in the same way. But what we are looking for at this point is a comparison between our design options. I have them on 4 different design layers, and I'm just telling it to collect the elements from my option 1 layer so I can see the results for that one. So the spaces will give us our total relevant floor area, and we can select a pre-configured system, and we can also have a look at our results now. You can look at these color bar type of results. We can inspect the building element, then we can see the results for roofs, walls, windows, doors, thermal bridges, and so on. Or we can have a look at a more detailed numerical outputs. That's my option 1. Then I can go back, tell NGOS to collect elements, not from layer option 1, but from option 2. Let's display the results tab so we can see them per building element. Let's hit update to see what's changed. We can see the numbers going up slightly, which is what we would expect. This is in line with our form factor analysis. After making the change on upper floor of option 1, that became our most efficient option, with option 2 slightly less so. This is mainly due to the fact we increased the total relevant floor area, while the building envelope surface remained similar, only slightly increased, and we can see that in our detailed results. Enegos validates the form factor calculations, so let's try to see if we get what we expect from options 3 and 4. Let's first collect elements from layer option 3 and update the results. The numbers shoot up once again, option 3 being our least compact form. Finally, let's see how option 4 performs in relation to other options. We'll repeat the process and collect elements from layer option 4. Go to Detailed Results tab and update. Now we see a drop in the demand and overall numbers. Let's just quickly have a look at that form factor worksheet to remind ourselves, and it's aligned to Enegos results. Option 1 is most efficient, option 3 least efficient, while 2 and 4 are very close, option 2 slightly better performing. So we can see how form affects the project at conceptual stages from the energy perspective, and how we can have a rough indication from very early on as to where we're going with our design. We can use this knowledge to make informed decisions as our design evolves and keep track of the effects that changes will have on the overall performance of the building. So let's move on in our design. We have evaluated different options and we went ahead to develop one of them. So I will skip that part of developing the model, and we are now looking at design development, which means that we are shaping the building. It's taking shape right now. We are going to go into some more advanced settings from the energy point of view, and we can still compare design options, and we are now starting to have some insight into our energy performance. I'll just quickly show you what the building looks like. You can see the plans for ground floor, first floor, roof plans, front elevation, and 3D view. So one notable difference at this stage would be the addition of windows and doors. Windows and doors are building elements and they are plug-in objects. You should really think of them in a similar way to the walls. They will also have styles, and I would again encourage you to use them. So you can set manual override U value instead of the automatic calculation, which is still preferable at this point because you might not know which exact window product you'll use to be able to give Enegos specific data to use in its automatic calculation. Again, those manually set values can come from building regulations, from Passive House, or they could be your own targets that you're looking to achieve. If I select one of these openings, the object info palette will tell me that it's a door in a wall. Here I can see the style of the door object, and there are lots of different parameters. What I want to talk about is shading. General shading means the general orientation of the opening. North-facing openings will have high general shading, south-facing ones will have low or none general shading. You can also specify a custom shading coverage percentage as well. Surrounding shading means context. So surrounding buildings, trees, party walls that might cast a shadow over the opening, and so on. Summer shading is a horizontal shading element above the opening. It could be overhangs, awning, bristlet, anything which is above the opening and is providing shading to it. Additional shading is, as you can see, interior or exterior blinds, foil, shutters, so on. So a combination of these four will vary for all of the windows and doors that we have, depending on the situation for every single opening. Anagos needs this input from you as designers in order to take shading into account, because it does not actually model sun paths when performing calculations. For example, if you model a horizontal element above this opening, it will make no difference to the calculation and to the shading of the opening below it. What will make a difference is these values. This is what enables Enagos to output results in a matter of seconds when you update your project settings, but it requires manual input from you to perform the correct calculation. And then we can go into the Enagos project settings, which look very, very similar to the previous stage, as we're still in the basic range of parameters. We're still using pre-configured usage, and now we need to specify the design layers that we are collecting. This is different. Building elements will now be a bit different than our previous four options. Building elements have a little more complexity. There is a lot more elements in here, but we will not be using all of the walls. For example, internal walls will not be taken into account. Parapet walls also. I have slabs, walls, roof, but now I have windows and doors as well. I can apply a filter to look only at windows and doors. Spaces now give total relevant floor area as a much more accurate number at this point in time. We are using the overridden U values for walls, slabs, roofs, windows, and doors that we set in the styles of these plugin objects. Our building elements are still generic, so from a thermal performance perspective, not much changes, but in general, at this stage, our project is more developed and more defined, so our results will reflect that. Looking at the overview of our results, we can see the building envelope performance and the performance per building element. That will tell us that our windows and doors account for a large percentage of that building envelope performance number. And that is something that is useful information and that helps with our design decisions as we move forward, and we can think about improving our design in that particular area. We could reduce the size of openings, or we can consider using more efficient external windows and doors. And let's have a look at the detailed results as well. Now, moving on into the next phase as our project progresses further, we'll fast forward to construction documentation and the stage where we add technical detailed definitions, and we look into advanced energy settings, and we will continue to look at component analysis. This is the phase where we can gain a proper understanding of our design from the energy performance perspective. This is what our building has progressed to. Not much has changed in the shape itself. Architecture has been defined in the previous stage, but from a technical perspective, we have added actual materials and thicknesses to our building elements. This is how ground floor plans and first floor plans look like. Roof plan front elevation, and the 3D view. It's time to look closer into the technical detailed definition of our building elements. And we can see here in the slab style settings what's changed. Our slab style no longer has generic components. We have now defined those to reflect materials they will consist of. When we open component settings, we can define components thicknesses and thermal conductivity, otherwise known as lambda. As lambda is a material property, there is a handy list here where you can look up values for common materials. If you know lambda values of materials you're using to be different to these, you can manually input a value and you can even add them to the list to be reused at a later time. What this means is that in Insertion Options tab and go Section, we will no longer ask it to take the overridden U value, but it will instead calculate the U value for us, based on all the building elements, component thicknesses and lambdas. There is one more parameter that you need to set for U value calculation to be accurate, and that is object boundary type. You can see the options available are ground contact slab, slab with unheated attic space above, slab at unheated enclosed space below, exterior slab facing up, or exterior slab facing down. This is due to the way U values are calculated. Unlike lambda, that is a material property, U value will depend on the position of building element in the envelope and on the direction of the heat flow. As you can see in this diagram, surface resistance coefficients will vary across horizontal or vertical surfaces like walls or floors or roofs, external or internal surfaces, like when you have an attic above or it's a flat roof. Good news is these coefficients are built into Vectorworks, so you don't have to worry about what those are. What you need to do is simply choose the correct boundary conditions of your building elements. Now let me show you the difference in our model. For the terrace, I have chosen roof as a function and exterior roof as boundary type. And for ground floor slab, floor as function and ground contact slab as boundary type. Wall is set as exterior wall. We continue looking at building elements. Next up are windows and doors. In a similar fashion, the style settings under Enegos tab, we will change U value from manual input to automatic calculation, and you will see the door type parameter become available. We can now choose from a number of configurations here that have different values. You can see what these are by clicking Edit List, and then you can select a particular door type. To show you an example, this is the one I created for this project, so we can see exactly what's been set for frame U value, thermal bridge glazing edge, thermal bridge wall insulation, solar heat gain factor, glazing U value, visibility transmittance, and air leakage. Coupled with structural opening dimensions, this is where Enegos will get the information about the thermal bridging of the openings, and these values will translate to thermal bridges calculation. Similarly, air leakage will inform air tightness calculation. Once in our design, we know exactly which door product we are going to specify. Then we can get this data from product data sheets, and then we can set all of these parameters. We can add a new door type configuration on this list, or we can duplicate a similar one, and then we can just modify the numbers as needed. The window settings are very similar. Let me just find a window style. In Enegos tab, we can see the only difference is it's not listed as a single type. The frame and glazing parameters are separate. We can still edit the list, and then we can see the parameters like U value, thermal bridge, and air leakage for the frame only. And then the glazing will have some different parameters, such as the solar heat gain factor, U value, and visibility transmittance. So once you've set all these up, and once you've told your window style to automatically calculate based on these parameters, but also based on the size of the glazing and the frame and so on, Enegos will automatically calculate the U value for your windows and doors. And then we have complete information of precise calculated U values of our actual building envelope. We can now move into the energy settings, and you can see that the dialog looks different. I'll just bring it up. Now we've moved into advanced parameters, and a whole new world of options appear. We can modify the configuration instead of using a pre-configured usage pattern. We can set the user profile, a residential building type, and dwelling as utilization pattern. Number of occupants can be estimated from the floor area, or we can input the values if we know them. We can set electricity usage and include or exclude different types of electrical equipment, like small appliances, have a dryer and not have clothesline evaporation. We can choose an equipment system and tell Enegos whether that's inside or outside of the thermal envelope. For example, if we have a washing and drying cupboard that is not in a heated space. Building envelope is pretty much the same like in previous stage, but now we can see thermal bridges here. That is in addition to what is automatically taken into account based on openings, as we previously talked about. We can manually input a percentage, or we could do the automatic calculation based on the thermal bridges list, where we can add a thermal bridge specifying quantity, length, and location, which could be any one of these. And we need to know the psi factor of the thermal bridge as well. Spaces are again what gives us our total relevant floor area and the volume. We can get some information about air tightness and the air infiltration change. We can set screening exposure of our building, and we can input the air tightness test values. Systems are showing our HVAC setup along with hot water. We can choose a ventilation system with different operation modes. We can set extract air ventilation only or heat recovery. We can include summer ventilation. And that's an interesting set of parameters because we can set the minimum acceptable indoor temperature and an overheating limit. Mechanical ventilation parameters are set here, how many air changes per hour we want and what is heat recovery capacity. You can specify summer ventilation operation, the temperature difference between inside and outside for the ground floor, upper floors, and for nighttime. Primary and secondary heating systems can be defined with the coverage percentage of each system. Perhaps we have a combination of boiler and solar. We can choose which boiler we will use, and you can even go into details for every one of these boiler settings or create a new entry on the list. There are a lot of parameters here, so I suggest sticking with presets or speaking to your mechanical engineer. Similarly, if needed, choose a cooling system. Hot water system settings again look similar. We can include a distribution system too, that being the pipework. Then finally, we can go look at results. We are already familiar with how they are displayed from previous stages. It's just that they're more accurate now as we know more about the building, so we can give more information to Enagos to work with. So for example, you can see we have a result for thermal bridges at this point. And we can also see that the biggest contributor to building envelope performance are windows and doors. So let's have a look at these doors, and you can see that they are still using manual input and the U value is 1.4. Let's change that to automatic calculation so it drops to 0.82 and see which kind of impact will having more efficient large glazing units make on our results. If we now go back to energy settings and rerun the calculations, we'll hit update and let's see if we can actually get improved results. You can see that it's dropped quite a bit, and you can immediately see the impact as I mentioned previously. It's very useful because it will give you results instantly. It's because it's based on a mathematical calculation model that comes from Passive House, rather than modeling actual solar parts together with geometry to obtain shadows, for example. As it's running a mathematical calculation, not building a model, that's why it depends on your input as designers. In terms of parameters such as shadow shading, additional thermal bridges, etc. But it won't occupy your memory or processing power while it updates the calculation, and you can see those results in seconds. Finally, to wrap up, we can export the results in Excel-friendly file format as comma delimited or tab delimited, so we can use the data and continue the energy performance evaluation in another software like PHPP. We can also create a label to tell us which rating we have achieved. This label is actually an intelligent object, and we can also tell it which data we want to see in the object info palette. I can select the whole performance overview set of parameters, and maybe let's add thermal bridges as well. And we can see from here, and we can use this data directly, for example, in a worksheet, just to add some more functionality and some more usability within Vectorworks. Finally, that brings us to the end. Thank you for joining me. To find out more about energy modeling in Vectorworks and in Enagos, have a good day.